I'll go ahead and get started. All right, so I thought today will be our last lecture on the topic of neural networks, and I thought we will take a look at a kind of a famous and classic data set for neural networks. And so let me just go ahead and clear out my environment. On on CCLE, I've uploaded a couple files here. One is to load the data, and one is the neural network itself. And here's a link to the MNIST dataset. Okay, and so the MNIST database, this is the official one, is a kind of a famous dataset. It's got 60,000 images or examples in the training set, and the test set has 10,000 images. And basically, this came a lot of early stuff was done because the post office wanted to automate kind of mail sorting, and they wanted to be able to scan zip codes. When people write zip codes on a piece of paper in an envelope, they wanted to say, like, okay, this zip code is 90210, and it should go to over here, and this zip code is something else, and it goes somewhere else. And so that's what a lot of this stuff started off with. And so anyway, this is the kind of the original MNIST database. It's because so much a lot of work has been done. It's very famous now, and you can find if you search for MNIST database, you're going to find all sorts of copies of it. This is the original, and you should stick to this. Okay. The thing is when you download it, you're going to get these kind of GZ files, and you're going to have to like unzip them onto your computer. You're going to put them into some directory. So I have them in the MNIST directory here, and these are the different files here. Okay. And what I'm going to do is this is the script to load the data. Okay. And this reads in the UByte data from the thing, which is, I guess, how it's going to get loaded. And so I'm going to call this, and I call load MNIST, and it takes a couple seconds, but it loads the data into memory here. And so test is a big matrix list, and train is a big list of matrices and stuff. And it also comes with this function show digit, which will show the image in kind of the plot window here. So we'll just go ahead and take a look at the first thing here, and the label on this image is 5. So in the training data, it comes with what the labels are and what the data is. So it comes with the input X and the output Y. And so and the input for this image is a vector. It's a vector of 784 values. Okay, vector of 784 values. A lot of them are zeros. Okay, and then we get 3, 18, 18, 18, 126, 136, and so on and so forth. And basically, when in the parts where ink has been detected and stuff, it's going to put in a number between 0 and 255. 255 for where there's writing, 0 for where there is not. Okay, and we can look at the plot of this. Okay, and this is the image, and it is the digit 5. Okay, and we can just kind of take a look at a couple other digits. So here's this one. The label on this image is a 0. Okay, And no surprise when I plot it, indeed it looks like a 0. Here's another image. Okay, here is, this image is labeled a 4, and this is the vector of 784 values. And when I plot it, this is what that number 4 looks like. This image is labeled as a 1, and that sure looks like the number 1. Okay. And this image is labeled a 9. And here's the 784 values. And when you plot it, it looks like this. Okay. And so to kind of illustrate what the what our neural network looks like, you know, I drew this picture a couple of years ago, but 3 Blue 1 Brown has this great video that shows. So he's using, you can see he has the image 9 loaded up on his screen, and you know, I have the exact same image here, and he has a beautiful animation showing how we're going to turn this into our neural network. So this is a 28 by 28 image. Let me make sure you guys can hear it. And
the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels.
So right now our data goes from 0 to 255. Later on in my code, I'm going to do exactly what he says, which is turn everything into values from 0 to 1. But I'm going to take the training data, this 0 through 255 value, and I'm going to divide everything by 255, so that everything will become a value between 0 and 1.
This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer.
Okay, so I just like that this part right.
4 neurons make up the first layer of our network.
All the pixels. Like that. Okay, so we've got our 784 values will form our first layer. This is our input layer, and there's 784 neurons there. And in his
now jumping over
in his neural network, he's got 2 hidden layers. I've chosen to keep it simple and just have 1 hidden layer. Okay, but as you see in this image, every node in this layer is connected to every single node in the following layer. Okay, and then every node here is connected to every node in the following layer. And so so just in your mind, or in our setup, we just have 1 hidden layer. Okay, I've got the input layer 784, the hidden layer I'm going to have 30 nodes here, and then the output layer I'm going to have 10 nodes like he has here. Okay, and each of these 10 nodes will represent a digit. I'll let Grant
to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers.
Okay, and so so we'll pause the video here, but this is what we have going on. With the output layer, we've got the digits 0 through 9 represented with nodes, and the reason for this is because we are performing a classification problem. We want to classify the input image as one of the digits, 0 through 9. Okay, so is it a 9? Is it an 8? Is it a 3? We want to be able to classify it as one of these digits. And you might be wondering, you know, why don't I just use one node in the output, right? On on Monday and last week, we looked at a neural network where we have one output. We said the inputs are hours slept and hours study, and the output is the score on an exam. And there we only had one node in the output layer. So, can I use just one node in the output layer here? Well, when you use one node in the output layer, the way the system measures how right or wrong an answer is it's going to measure the distance between our prediction and the correct answer. So if the correct answer is 9, then if the system guesses 9, that's good. It's going to say you made no error, right? But if the system guesses it's an 8, it's going to say you were off. You were off by a little bit. And if the system guesses it's a 1, it's going to say you're off by a lot. Okay, and it's now, so we're going to be set up in such a way that we punish guesses like 1 that are have a large difference between 1 and 9. We're going to punish that guess more heavily than we punish the guess of an 8. Okay, so we're going to say 8 was pretty close to 9, so that's not punished hard. But 1 is far away from 9, so that's going to get punished heavily. That makes sense if we're trying to predict some kind of numeric output, like how much money did you spend? If you plan your budget and your budget comes in very close to what it actually was, even if it wasn't perfect, you'll be happy. Okay, but if the budget was way off, then that's upsetting. But in this case, think of this: even though the outputs are the digits 0 through 9, they're not actually they're not numeric in the sense that 8 is less wrong than 1. And when we're classifying digits, if the correct answer is a 9 and we guess 8, that is completely wrong. If the correct answer is 9 and we guess 1, that is also completely wrong. The guess of a number 1 is not more wrong than the guess of a number 8. Okay, so when you have a classification problem, each category that you need to predict will need its own node. And what we want is to say the output that we predict is going to be zeros for everything else, and it's going to be a 1 for the correct answer. Okay, sorry. So that's what we want. We want zeros for everything here and a 1 for the correct answer. And we don't want to say 8 is more or less wrong than 1. We want to say 8 is wrong, 7 is wrong, 1 is wrong, that they're all wrong if we guess the wrong thing. So what we have to do is we're going to set it up so each of our answers will get turned into 10 nodes. Okay, and so that's what this function is going to do. I called it vectorize, but basically what it does is it takes the label j, and then it sets up kind of a vector k, which is 10 zeros. And for the correct label, which will be j plus 1, it's going to replace it with a 1. So let me just kind of show you what this does. Okay, so so I applied that function, this vectorize function, to our training labels. Okay, and for the first 6 rows, this is what it outputs. Okay, so the first digit, it's got basically all zeros, and then it puts a 1 in this column and zeros over here. Okay, and that corresponds to the label 5. Okay, because if you think of this, this first column is digit 0, and the last column is digit 9. So it goes. So we got all zeros here, and then the 6th column, which corresponds to digit 5, is a 1, and everything else is a 0. Okay, and this the next digit in our data is a 0, And so it gets a 1 in this first column, and everything else is a 0. The next digit is a 4, and so it's zeros for these columns. It's a 1 for the column that corresponds to 4, the zeros for everything else. Here's a 1, we get zeros over here, and this. So this is we're going to tell the system that we want to predict all zeros and one node as a 1. That's what we want it to do here. Okay. All right. So the next part is basically the code that I showed you on Monday. Okay. So on Monday we worked through the rest of the back propagation, and we coded everything up. Okay. And so so there we defined a sigmoid function. Okay. And then we defined the derivative of the sigmoid function, which we called sigmoid prime. And then and we also have a cost function, which is going to calculate the sum of the squared errors. So we calculated the difference between the actual value and the predicted values y hat. We square those differences and we sum them up, and that's going to be the cost function. Okay, and then with Monday's code, I kind of left it set in this way. And so our input layer, we have 784 nodes in the input layer. We're going to have 10 nodes in the output layer, and then I have 30 nodes in the hidden layer. And this number 30 is just an arbitrary number. I think, and I just have one hidden layer. And again, that's kind of an arbitrary choice. Well, mostly because I wanted to keep it simple. I didn't want to have too many hidden layers in our neural network here. Okay, and so what I'm going to do is I'm going to start off with just some random values. I'm going to just say generate a whole bunch of random uniform numbers, and we're going to populate our initial weight matrix. We have our two weight matrices, weight matrix 1 and weight matrix 2. We're going to populate our two weight matrices with just a whole bunch of random numbers. Okay. And so so we've got a whole bunch of these values here. Okay, so we've got the start here, and then what we're going to do is we are going to do gradient descent. Okay, we're going to do gradient descent, and so we learned about that. So we on Monday we went through the calculations or the derivations, and we got the gradients. And we calculated the gradients on Monday, and it came out to be this, right? And so we're going to apply gradient descent. Now I'm going to do something slightly different here, okay? And it's because I've got 60,000 images in my training data set. And so if I tried to do the calculations on the full 60,000 image training data set, it is going to not break my computer, but my computer will take a very long time to calculate, do all of the calculations, because I've got 60,000 of these images to work through. Or basically my matrix, the input X matrix is n by how many columns, right? I've got 784 columns because it's 28 by 28 pixels. And I'm going to have 60,000 rows. So it's going to be 60,000 by 784, which is, how big is that? 60,000. That's 6,000. 60,000 times 784. Okay, that's like 47 million values. 47 million values in a matrix. That's really big. I'm gonna so it's gonna clog my computer. So what I'm going to do is I'm going to take my training data and I'm going to split it up into what we call batches. We're going to have, I'm going to take batches of 10 images. And those 10 images, I'm going to calculate the gradient based on those 10 images. And and then so I calculate the gradient based on those 10 images. So it's only 10 by 784, a much more manageable 7,000, 8,000 elements. So I take those 10 images, I calculate the gradient, and I'm going to take a step in the opposite direction of the gradient and go downhill. And then what I'm going to do is I'm going to change the 10 images. I'm going to just shuffle them up, and I'm going to take a different batch of 10 images. I'm going to calculate the gradient based on the next 10 images, and then we'll take a step downhill. And then we take another set of 10 images. We're going to calculate the gradient on another set of 10 images and take a step downhill. And we will continue doing that until we go through the full training data set. Okay, and so so I'm going to end up taking 6,000 steps downhill, but I'm going to see each image in the training data set only once. Okay, because I'm going to do 6,000 iterations of 10 images each. So I'm going to see each image in the training data set just once. But and I could repeat this again, but I think it's fine. Okay, so so that's what I have written on here. Okay, so so the way I've done this is I'm going to shuffle up the 60,000 rows. Okay, and then I create a sequence called J sub. Look, first 10. And it basically counts by 10s. It goes 1, 11, 21, 31, 41, 51, 61. Okay, and the batch size is going to be 10 images at a time. And let me just show you, for I equals 1, what I'm going to do is I'm going to say, let's just take the kind of the first 10 rows here. So if I say, I is going to be 1, and then it creates a vector from I to I plus batch size, so that's going to be 11 minus 1, so that's going to be 10. So this is going to create the vector 1 through 10. Then when I is 11, it's going to start at 11, and it's going to go 11 plus batch size being 10, so that's going to be 21 minus 1, 20. So this is going to go from 11 to 20, and then the next one will be from 21 to 30, and then from 31 to 40, so on and so forth. Okay. And then we're going to subset the training data to just those 10 selected rows. Okay, we're going to take those 10 selected rows, and then here we scale them down. So we divide everything by 255, so everything's a number between 0 and 1. Okay, and then we take our row vector. Okay, so this is basically what we're going to have. So when I run this, here are my rows, and here's going to be X and Y. So if I say dimensions of X, I've got 10 values, or 10 entries in my X row, but each entry has 784, is a vector of 784, right? So X will have, right now, have a dimension of 10 by 784. And then Y, the dimensions on Y, we've got 10 entries, so it's N. And then I have 10 nodes in my output layer, so Y is going to be a 10 by 10 matrix there, okay? And then I do forward feed, okay? So forward feed is, we're going to take our X matrix, my 10 by 784 matrix, and I'm going to multiply it by my first weight matrix, W1, which is 784 by 30, okay? And then so that creates a matrix Z. So Z is going to be 10 by 30. I apply sigmoid to Z, okay, to activate everything. All right, and that produces A2, which will be 10 by 30. Then I multiply it by my second weight matrix. My second weight matrix is going to be 30 by 10 because I've got 10 nodes in the output layer. So we're going to take this. We're going to get 10 by 30 by 30 by 10. And the output will be a 10 by 10. I apply the Y sigmoid to get that, and I get my Y hats. Okay, so this is just the forward feed part that we did in on Monday. So we X times W, apply the sigmoid function, A times W, apply the sigmoid function, and here we get Y hat. Okay, And then so once I have my y hats, now I calculate my gradients, okay? And so we did all of the back propagation and we calculated the gradients. And so this is the code pretty much straight from Monday's lecture where I calculate the gradients, okay? And so I get my gradient here and I get my gradient for the first weight matrix there. So we're going to calculate the gradients. And then once we calculate the gradients, then we do gradient descent, which takes our current weight matrix W1, subtracts off the scalar times the gradient, and then we take our current weight matrix W2 and subtracts off the scalar times the gradient, and it updates our two gradient values, okay? So, you know, right now, my current weight matrices is, you know, complete trash because it's just completely random values here. I just used RUnit to give me these values. And if I just do it kind of for the first values here, my predictions are going to be, these are my predictions. My predictions are complete garbage. Remember, what we want to see is something close to, we want, for the first image, what is my first image? Let's see. Well, I don't know what my first image is here, but you know, if the label is a 9, we want to see all zeros over here and a 1 right here, okay? Which is not going to be the case right now. But we would go through and we would go calculate our gradients and then improve our weight matrices using these gradients here. Okay. All right. Let me just pause here and just check in with you guys and see if this makes sense. If you're following along, give me a green check mark. If you've got questions, please enter them in the chat or raise your hand. And then let me also give you my today's first quiz answer is E. First quiz answer is the letter E. Okay, well, most of you gave me a green check mark, so that's good. And I hope the rest of you are doing okay and following along. All right, okay, so I'm going to go ahead and I'm going to run this code then, okay? So let me just run everything. Okay, so it's going to take a couple seconds. It's got 60,000 images to run through, but it's done now. Okay, so it's done. Okay, and remember, all we've just been doing just simple operations. I'm not using any kind of package, just doing some matrix multiplication. Okay, and every time I run it, or with each iteration, I'm just changing what my W1 and W2 matrices should be. Okay, so now let's test how it performs, okay? So I'm going to take my test data, okay? So I'm going to take the test data and I scale it down. So I'm going to call this XT, all right? And let's go ahead and take the training matrices that we've created. So our weight matrix W1 and W2 have been trained on the training data. Okay, so so our weight matrices W1 and W2 now have values that have been adjusted using gradient descent. Okay, so we ran through this, and all this did was just basically do gradient descent. It just keeps updating W1 with the gradient and W2 with the gradient. And so now we have the values W1 and W2 as trained by gradient descent, okay? And then so we'll go ahead and we'll run our training data through this, okay? So we take our training data here and we go and we multiply by W1, apply the sigmoid function, multiply by W2, apply the sigmoid function, okay? And so this is what my y hat matrix looks like. So let's just kind of take a look at the first 5 rows here. Okay, so this is kind of hard to read. So let me go ahead and I'm going to just round to, like, let's say 4 decimal places. Okay, or maybe even just 2 decimal places. Okay, so here we go. All right, so with 4 decimal places, okay, we're getting values. We get a bunch of values. With 2 decimal places, it's even more clear. We can see we're getting values that basically round down to 0. Okay, and then this column is I guess 0.9998. Basically, it's predicting a value here, and then everything else is a 0. The second row, we've got zeros over here and zeros over here, and the highest value I have is this column with a 0.89. So remember, in our training data, we told it we want pretty much each row to have almost all zeros and one of the columns to be a 1, and that's what we have. We've got something pretty close to that. Okay, I've got a 0 here and a bunch of zeros over here, and this column is a 1. Here I got this column's a 1 and pretty much all zeros. Got a bunch of zeros and a bunch of zeros in a column of a 1. Okay, and so this is what we've predicted. And then so to turn these into guesses, right? So remember, this column, this first column corresponds to the digit 0, and this last column corresponds to the digit 9. So I'm going to tell R, tell me which column is the max. Okay, and that'll say it's the max column, and then we're going to subtract off 1. So that's going to be my guess. Okay, so my guess for the kind of the first 5 entries is it's guessing a 7, a 2, a 1, a 0, and a 4. Okay. All right. So let's go ahead and let's just see if if we did a good job, right? So here I guess the first entry we guessed is a 7. Okay. We pretty much have all zeros. Okay. And it's not like perfectly 0. We got 0.0024, but pretty close to 0, and then something pretty close to 1, 0.9998, right? So we've guessed a 7, and let's see what the image looks like. Okay. Yep, that looks like a 7 to me. Okay. And so basically, it's just taking this input. Visually to us, we recognize this as a structure. We see the 7 here, but remember, the computer isn't seeing the image the way we do. Okay, it just sees a vector of 784 numbers. Okay, it just says, remember, all it's seeing, okay, all it is seeing is just seeing this, right? So if I gave you this vector of 784 numbers, would you recognize that this is the number 7? In this form, probably not. You'd have to see it visually. But the computer just takes this vector of 784, it runs it through the matrix using this, and the matrix operations and multiplication and the applying the sigmoid function, and it gets a prediction here. Okay, let's take a look at the next one. It guesses a 2, and let's just see what that image looks like. And yep, that looks like the number 2. Okay, the next image, it guesses a 1, and indeed, when you look at the image, it looks like the number 1. Here it's guessing a 0, and when we create the image, or when we look at the image itself, yeah, this looks like a 0. Okay. I can't see your guys' faces, but this is impressive, right? This is really cool. It's just taking our inputs, and it's making predictions, and it's correctly guessing what those numbers are. Okay, and again, to make the prediction, all it's doing is it's just taking the new test data, a vector of 784 values, and it's just multiplying it by a matrix, applying a function, multiplying that by a matrix, applying a function, and then saying, which column is the biggest number, okay? And based on that, we're getting predictions. And it all came down to what values did I put inside this first weight matrix, and what values did I put inside the second weight matrix, okay? And so all of the effort is put into there, and sorry, my dog's drinking water over here. I don't know if you heard that. All of this, all of the effort goes into deciding what these matrices W1 and W2 should be, and that was done back here in this step when we did the training here, this for loop where it goes through all of the training data and it applies gradient descent to take steps downhill. Okay, so let's, I don't know, are you guys impressed? Okay, so let's go ahead and just take a look at its overall performance. So we'll take a look at the, here are the actual values. Okay, the actual values are found in the test data set. And then we will compare that to our guesses. Okay, so I'm going to create a data frame out of our actual values versus our guesses. So, you know, you can look at the head of the kind of the results data frame. Okay, and so far we've got perfect guesses for the kind of the first 6 rows. And then what I'm going to do is I'm going to table these, which will create what we can call a confusion matrix. Okay, and what we want to see is values down the diagonal. Okay, values down the diagonal means when it was when the actual value was a 0, we correctly predicted it was a 0 941 times. When the actual value is a 1, we correctly predicted it's a 1, you know, 1100 times. When the actual value is a 2, we correctly predicted it's a 2 966 times. The off-diagonal elements, these are the times when we made a mistake, okay? So sometimes when the actual value is a 2, we predicted it was a 3. That happened 10 times, okay? In our training data set of 10,000 images. So, so you know, we made a few mistakes, and we can see, okay, how many values total are along the diagonal versus not along the diagonal. And so just with our very simple matrix with one hidden layer and 30 nodes in the hidden layer, which is quite a simple architecture, we've achieved around 92-93% accuracy. Okay, 92.5% accuracy. So that's not too bad. I'm feeling pretty good about that. But yeah, certainly we can get better improvement and things like that. But that would require a little bit more, probably a slightly different architecture as far as neural networks go. Okay, so again, right now we just have a very simple neural network design where there's one input layer, one hidden layer, and one output layer. And you can have multiple hidden layers. You can change things up. Right now, our design is what we call a fully connected neural network, in that every node in this layer is connected to every single node in the next layer. And there's other designs where it's not fully connected, where only some of the nodes connect to the next layer. There's different things you can do at each step. There's like, you can pool some of the values together. You can do what's called a convolution and things like that. There's different things that can be done to neural networks, and you can take an entire course, or you can devote your entire career to researching neural networks. But here, this is just a very brief and light introduction to the subject. Oh, here I've got, let's just take a look at some of the mistakes we've made. So, we made a mistake on this particular image here. So on this row, it's the number 3, and our guess was, we guessed a 2, which was wrong. Okay, we can try like another. Let's try just another image here. We guessed the true value is a 4, and we guessed a 6. Okay, so you know, and some of these we can say, all right, I can understand how you would have trouble reading something like that, right? The true answer is a 7, and we guessed a 2. Okay, and we're like, yeah, I guess, okay. So anyway, we could kind of understand some of these mistakes that, probably a lot of these things are like just results of messy handwriting and stuff. But anyway, again, this is just a very simple introduction to neural networks. This is going to be our last lecture on the topic of neural networks. But I thought it fits in well with the theme of kind of computation for statistics, computation and optimization, applying gradient descent for optimization, and matrix calculation, certainly that was involved there. This is technically not like a required topic for 102B. If you look at the course description, there's no mention of neural networks, and that's fine. But I thought it was a neat topic, so I liked to bring it up and mention it in our course. Your next homework assignment is going to cover neural networks, and so please go ahead and get started on that. That's been posted, and I don't know. I hope you enjoyed. I hope you enjoyed this, and again, I think just one thing I think is so cool is that we've achieved this using just matrix operations. We didn't need to do any kind of fancy packages or anything like that. There are packages for creating neural networks, and it will do all of this stuff. But sometimes when you use a package, everything kind of becomes a black box, and we don't really know what's happening. I mean, that's the truth in this case, in that like we don't quite understand what's happening inside the matrix, like how the values in W1 and W2, we don't really know what those values themselves mean, but we can clearly see just the matrices being multiplied together versus just asking a computer package to do this for you. So anyway, that's all I have on neural networks. I don't know. Did you guys have any questions? Oh, second quiz question is B. B as in bear or boy. Second quiz question is the letter B. Is that good? Okay. Well, all right. We'll end there then, and have a good weekend, you guys. And we'll see you guys on Monday. We'll pick up on another topic on Monday. Give me a few days to get your exams graded. I still have to kind of schedule a grading session with my TAs and graders, and we'll go through your exams and whatnot. So, all right. Well, have a good weekend. We'll see you guys on Monday.